In a striking and unprecedented surge of seismic activity, the planet has recorded 397 earthquakes of magnitude 5.0 or greater within a single 30-day period. This figure more than doubles the usual monthly global average, which typically ranges between 130 to 180 such events. The scale and timing of this escalation suggest that what is occurring beneath Earth's surface is far from routine. This is not simply a statistical anomaly or isolated geologic turbulence. Rather, it is a synchronized, global-scale reaction, one that aligns with deeper geodynamic patterns and theoretical frameworks. Among the most significant developments in this recent burst of activity is the massive rupture near Kamchatka, a magnitude 8.8 event that alone underscores the gravity of the situation. Alongside this, powerful quakes have struck deep within the Kuril Trench, as well as regions near Tonga, Peru, and Japan. These are not surface tremors, but profound tectonic shifts occurring at substantial depths, shifts that indicate increasing instability along key subduction zones. Simultaneously, areas known for their tectonic boundary edges, such as Turkey, Italy, and the eastern United States, have experienced elevated stress and movement. These craton edge stresses are characteristic of periods when Earth's internal forces attempt to redistribute pressure across ancient foundational rock structures. Volcanic systems, too, are responding. Surges have been observed in regions like Alaska, Hawaii, and Indonesia. These surges suggest more than mere coincidence. They point toward an interlinked response across various geological domains. Supporting this view, electromagnetic monitoring systems, including data from the JOES satellite and the RT magnetometer, have recorded distinct disruptions in the electromagnetic field, anomalies that frequently accompany significant shifts in Earth's internal structure. This global tremor spike aligns with a specific astronomical cycle, the zero-key 40.58-day Venus resonance window. According to proponents of the core displacement and geodynamic rebalancing theory, this resonance plays a role in modulating internal torque within the planet. The theory posits that gravitational and electromagnetic interactions between celestial bodies can influence the Earth's mantle and core behavior, initiating chain reactions that release stress and reconfigure the distribution of mass inside the planet. This process is not immediate, nor is it easily reversed. Once initiated, it cascades through the system until a new internal equilibrium is reached. Historical parallels reinforce the seriousness of this pattern. The triple rupture of the New Madrid Fault between the years 1811 and 1812, the devastating Hoei quake in Japan in the year 1707, and the monumental magnitude 9.5 Chile quake in the year 1960, all occurred during periods of similar multi-system geologic activation. The evidence suggests that the current moment marks more than a peak in natural disasters. It signals the onset of what has been termed Phase 5. In the year 2024, a groundbreaking scientific study revealed that the Earth's inner core, long considered one of the most mysterious and inaccessible regions of the planet, has not only slowed its rotation in recent decades, but has also changed shape. Published in the journal Nature Geoscience, the research marks a significant departure from previous assumptions, which held that changes in the core's rotation and its shape could not occur simultaneously. This new understanding opens an important doorway into the mysterious dynamics taking place at the very heart of our planet and has major implications for our comprehension of Earth's internal processes. The inner core is a solid metallic sphere composed mostly of iron and is located at the exact center of the Earth. With a radius of approximately 1,220 kilometers, it was formed more than 1 billion years ago through the slow crystallization of iron from the surrounding liquid outer core. It is the hottest region of the planet, with temperatures ranging from 6,000 to 7,000 degrees Celsius, hotter than the surface of the Sun. The pressure it endures is equally extreme, reaching around 3.5 million atmospheres. Despite these harsh conditions, the inner core performs vital functions for the geodynamics of the entire planet. Among its most important roles are generating Earth's magnetic field and promoting plate tectonics, two factors that are crucial for maintaining conditions suitable for life on the surface. The Earth's magnetic field, which shields the planet from solar radiation and cosmic particles, is powered largely by the process of convection in the liquid outer core. This convection is, in turn, driven by the gradual growth of the solid inner core at a rate of roughly 0.5 millimeter per year. As the inner core crystallizes, it releases heat and light elements into the outer core, setting up the convection currents responsible for the magnetic field. In addition, the inner core helps to regulate the flow of heat through the Earth, influencing surface conditions in complex and subtle ways. Because of these interconnected systems, understanding the behavior and evolution of the inner core is essential for comprehending the broader mechanics of the planet. Until recently, most studies focused on the rotation of the inner core, particularly its ability to spin at a different rate from the rest of the Earth. Around the year 2010, scientists observed that the inner core, which had previously been rotating slightly faster than the rest of the planet, began to slow down. While that alone sparked extensive scientific interest, the most recent research has taken that curiosity even further. For the first time, a team of international researchers has shown that not only has the inner core's rotation changed, but its shape has also shifted over the past 2 decades. This discovery is particularly surprising because prior models did not allow for these two phenomena to occur simultaneously. The methodology behind the study is rooted in a well-established technique in seismology involving the analysis of seismic waves generated by what are known as doublet earthquakes. Doublets are pairs of earthquakes that occur years apart, but share the same hypercenter and focal mechanism, and are recorded by the same seismic stations. This unique configuration allows scientists to detect extremely subtle changes in the Earth's interior by comparing the travel times and waveforms of these seismic events. Any differences in the waves between the two events can reveal variations in the internal properties of the Earth, including changes in the speed of rotation and even physical deformation. John Vidal of the University of Southern California and his research team employed this technique using seismic data from the Eielson and Yellowknife seismic arrays in the United States. The data originated from earthquakes in the South Sandwich Islands, some of which occurred before and after the inner core's slowdown in the year 2010. By examining how seismic waves passed through or around the inner core during these events, the researchers were able to identify patterns that indicated more than just a shift in rotational speed. They found that seismic waves, which passed directly through the inner core, remained consistent over time, whereas those that only skimmed its surface displayed noticeable differences. This pattern strongly suggests that the shape of the inner core itself had undergone a subtle transformation. The implications of this finding are profound. If the inner core is not a perfectly uniform sphere, but rather one that can deform over time, it changes how scientists interpret the long-term behavior of Earth's innermost region. According to the study, the shape change may be influenced by forces such as density anomalies at the bottom of the mantle or convective flows in the outer core. These forces could exert pressure or drag on the inner core, causing it to stretch or compress in localized areas. Though the team has not yet been able to quantify the exact degree of deformation, the mere presence of such changes challenges long-standing assumptions in geophysics. Perhaps even more intriguingly, the combination of both rotational slowdown and shape deformation could provide new clues about the thermal and compositional structure of the inner core. It may also allow scientists to revisit and revise the multi-decade history of the inner core's behavior in relation to the rest of the planet. Since the Earth's magnetic field, plate tectonics, and even climate are linked in complex ways to the movement and properties of the core, any deeper insight into this hidden region has the potential to refine our understanding of planetary dynamics. The discovery also invites new questions. For example, how frequently do these shape changes occur? Are they part of a larger cycle? Could they influence, or be influenced by, events occurring in the outer layers of the planet? Future research will likely explore these questions with more advanced models and even higher resolution seismic data. One possible avenue of investigation will be to monitor additional doublet earthquakes across various global fault lines, providing a more comprehensive map of how the inner core evolves over time. Over the past decade, scientists and seismologists have observed a noticeable and concerning trend, a global surge in the number of what are termed great earthquakes. Defined as seismic events of magnitude 8.0 or higher, these powerful quakes have been occurring with unusual frequency, challenging prior assumptions about the predictability and recurrence of large-scale tectonic activity. Between the years 2004 and 2014, the Earth experienced 18 such earthquakes, representing a nearly 265% increase compared to the average frequency over the previous century. This period, which saw an annual uptick in seismic energy release along major subduction zones, has raised questions about potential implications for fault lines that have remained quiet, particularly in the Pacific Northwest of the United States. The data, presented at the annual meeting of the Geological Society of America in Vancouver, British Columbia, painted a compelling picture. The historical baseline for great earthquakes, calculated from 71 events over the span of 100 years, suggested a global norm of roughly one great earthquake every 1.5 years. The sudden clustering of 18 such quakes within just one decade broke that pattern and prompted renewed investigation into possible global tectonic shifts. Though the increase might appear alarming, scientists like Thorn Ley, a distinguished professor of Earth and planetary sciences at the University of California, Santa Cruz, cautioned against overinterpretation. Ley emphasized that while there was a clear surge in high-magnitude earthquakes, the total number of earthquakes of all magnitudes had not increased significantly. This, he suggested, could indicate that certain plate boundaries were simply catching up on long-standing tectonic stress that had accumulated over time. Ley and his colleagues noted that great earthquakes sometimes appear to trigger one another, particularly when they occur along the same subduction zone. The Sumatra Andaman earthquake of late December 2004, for instance, was followed in close succession by major events in 2005 and 2007, all along the same plate boundary. These sequences indicate a type of domino effect, where one rupture increases strain on adjacent sections of the fault, potentially bringing them closer to their own failure point. This interconnected behavior is largely constrained to individual fault systems, meaning that a great earthquake in the Western Pacific is unlikely to directly trigger one in North America. Nevertheless, these global events serve as a reminder that similar conditions exist elsewhere, specifically in regions like the Cascadia subduction zone along the coasts of Washington, Oregon, and northernmost California. The Cascadia subduction zone, where the oceanic Juan de Fuca plate is diving beneath the North American plate, remains one of the most closely watched and potentially hazardous seismic regions in the continental United States. Geophysicists believe the fault is currently locked by friction, with strain steadily building as tectonic forces press the plates together. This strain will eventually be released in a large seismic rupture, though no one can predict precisely when this will occur or how extensive it will be. According to Ley, the offshore fault appears fully primed for a significant earthquake, the timing of which is impossible to determine with any certainty. Adding to this complex picture, Peter Shearer, a geophysics professor at the Scripps Institution of Oceanography, notes that the last decade has provided vital insights into the unpredictable nature of subduction zone earthquakes. He explains that these great quakes can rupture in multiple ways, and so far, no single model accurately predicts how or when they will behave. Some may rupture all at once across a vast section of fault, while others may release in a series of staggered events. This unpredictability makes forecasting a challenge, especially for regions like Cascadia that lack historical written records of seismic activity. The most concrete information about past Cascadia earthquakes comes from geological evidence and distant historical documentation. Benjamin Horton, a professor in the Department of Marine and Coastal Sciences at Rutgers University, has led efforts to reconstruct the region's seismic history by studying mud layers and sediment deposits along the coastal zones of British Columbia and the northwestern United States. Through trenching and core sampling, Horton and his team have identified signs of 12 major earthquakes over the past 6,000 years. These findings indicate an average recurrence interval of approximately 500 years, although Horton cautions that the intervals vary significantly, from as short as 350 years to as long as 1,000 years. One of the most fascinating discoveries regarding Cascadia's seismic past comes from across the Pacific Ocean in Japan. The most recent known great earthquake in the region occurred on the 26th of January in the year 1700. At the time, European settlers had not yet reached the Pacific Northwest, so there are no written local records of the event. However, Japanese historical documents describe a mysterious tsunami, later termed an Orphan Tsunami, because it arrived without any local seismic activity in Japan to account for it. This anomaly led scientists to connect the tsunami to a massive earthquake on the other side of the Pacific, ultimately confirming the magnitude and location of the event in Cascadia. Based on sedimentary and geological evidence, that quake is believed to have had a magnitude between 8.9 and 9.2 and may have ruptured as much as 600 miles of fault line stretching from Northern California to British Columbia. This scale is similar to the 2004 Sumatra earthquake, providing an analogue for the kind of event that could occur again in Cascadia. As Shearer explains, subduction zones are particularly capable of generating massive earthquakes because their faults are both long and wide, slicing at shallow angles through Earth's crust. This geometry allows for the release of far greater amounts of energy than is possible along the more vertically oriented faults found in strike-slip systems like the San Andreas Fault. In addition to onshore evidence, Horton's research extends into the ocean floor, where signs of past tsunamis and sediment displacement reveal further proof of great earthquakes. Underwater canyons off the Pacific Northwest coast preserve layers of sand and debris deposited by shaking and water displacement. These layers are useful markers, allowing scientists to trace tsunami events and match them to their likely sources. The combined evidence from land and sea suggests that while large earthquakes in Cascadia may not occur frequently, their effects are catastrophic when they do. Despite the detailed study of past earthquakes, Horton emphasizes that the irregularity of recurrence intervals makes precise prediction impossible. The average of 500 years may provide a general guideline, but it does not mean the region is safe for another 2 centuries. In fact, given that the last rupture occurred more than 300 years ago, some scientists argue that the region may already be within the window of increased seismic risk. In conclusion, the worldwide surge in great earthquakes over the past 10 years serves as both a scientific mystery and a public warning. While the increase may be due to statistical coincidence or the natural release of long-accumulated stress in certain tectonic regions, it underscores the importance of understanding and preparing for similar events in other vulnerable areas. The Cascadia subduction zone remains a prime candidate for a future great earthquake, with mounting geological evidence pointing toward a locked and loaded fault system. Advances in seismic monitoring, geological analysis, and historical reconstruction are providing valuable tools for scientists to refine their understanding, but the precise timing and nature of the next event remain unknown. What is clear, however, is that the Earth's tectonic forces continue to operate on scales far beyond human timelines, and staying prepared is not just wise, but necessary. The devastating 7.7 magnitude earthquake that struck Myanmar on March 28, 2025, left a trail of destruction across the country. Centered near Mandalay, the nation's second-largest city, the earthquake was one of the most powerful recorded in the region in recent decades. It caused significant structural damage, injuries, and loss of life. However, amid the devastation, an unexpected revelation emerged from the earth. In Tada'u Township, roughly 10 kilometers from Mandalay, the tremors unearthed a long-buried and massive archaeological structure, believed to be a royal water palace from the Konbaung dynasty. The earthquake-induced geological shifts fractured the land in several locations, exposing areas that had been untouched for centuries. This movement brought to light a series of ruins near the ancient city of Inwa, historically known as the City of Gems, a site that once served as the imperial capital for multiple Burmese kingdoms. According to a statement from the Department of Archaeology and National Museum, the structure unearthed appears to be part of a royal water residence or palace, used during the height of the Konbaung dynasty. Although initial hints of the site had surfaced as early as 2009, when locals involved in brickmaking stumbled upon what appeared to be an old staircase shaded by mango trees, it wasn't until the earthquake's upheaval that a clearer picture of the structure began to emerge. The force of the quake created new fissures and revealed buried segments of architecture, including stairways, brick platforms, and what appears to be part of a handrail. This led to immediate interest from archaeologists and prompted test excavations, which began on April 6, 2025, under the direction of the Mandalay branch of the Department of Archaeology. Early measurements from the site include a 10-foot-long brick platform and an 18-inch riser step. These dimensions suggest the structure was built to accommodate a grand entrance, likely intended for ceremonial or royal use. The staircase, now partially visible, hints at a grander architectural framework that remains buried beneath layers of soil and debris. Other uncovered features, such as the base of pavilions and carefully aligned brick footings, align closely with historical illustrations preserved in palm leaf manuscripts from the Konbaung period. The Konbaung dynasty, also known as Burma's Third Empire, ruled from 1752 until 1885, when British colonial forces annexed the region following the Anglo-Burmese Wars. This dynasty marked a significant period of cultural, military, and political development in Myanmar's history. During their reign, the monarchs of the Konbaung dynasty were known for constructing grand royal cities and elaborate palaces that reflected their power and prestige. The discovery of a water palace structure tied to this era not only confirms the historical narratives preserved in Burmese literature and oral tradition, but also provides tangible evidence of the sophisticated engineering and architectural prowess that characterized the time. The site's location near Inwa is particularly significant. Inwa had served as an imperial capital for centuries, beginning in the 14th century under the Ava kingdom and continuing into the Konbaung era. The city was repeatedly sacked, rebuilt, and then ultimately abandoned in 1839, following a series of catastrophic earthquakes. For historians and archaeologists, the emergence of these ruins in 2025 echoes a poetic cycle. The same natural forces that once brought an end to Inwa's prominence have now, nearly 2 centuries later, helped unearth the remnants of its regal past. Experts believe that what has been revealed so far may only be a fraction of what lies beneath the surface. With foundational remnants, steps, platforms, and architectural elements already visible, hopes are high that continued excavations will lead to the discovery of inscriptions, artifacts, or possibly even ceremonial objects that can further illuminate the purpose and significance of the site. Moreover, there is growing interest in how the structure might have functioned as a water palace, possibly featuring moats, reservoirs, or artificial lakes designed for royal recreation or spiritual rituals. The timing of the discovery also comes during a renewed period of global archaeological interest in Southeast Asia. In recent years, technological advancements such as light detection and ranging and drone surveying have enabled researchers to uncover vast temple complexes, ancient cities, and forgotten roadways buried beneath jungles and fields. The Myanmar earthquake, tragic as it was, created a unique opportunity for researchers to conduct real-time assessments in a historically rich but often underexplored area of the country. Local residents in Tadayu have responded with a mix of reverence and curiosity. Some elders recall stories passed down through generations about hidden structures and lost staircases in the region, suggesting that oral traditions may have preserved memories of this site even after its physical presence was buried. The community has also expressed pride in the cultural value of the discovery, recognizing it as a connection to their historical roots. As efforts to excavate the site continue, both the national government and international observers have emphasized the importance of preserving the ruins. Given Myanmar's tumultuous recent history, which includes both natural disasters and political instability, protecting and studying this site presents logistical challenges. Nonetheless, the Department of Archaeology and National Museum has pledged its commitment to further research and conservation. In cooperation with academic institutions, there are plans to map the site comprehensively and secure the area to prevent looting or unregulated tourism. What began as a tragedy on March 28, 2025, may ultimately result in one of the most significant archaeological discoveries in recent Myanmar history. The unearthing of the Konbaung-era water palace stands not just as a testament to the destructive power of earthquakes, but also as a reminder of the deep, layered history that lies hidden beneath the surface of our modern landscapes. As excavation and preservation efforts move forward, researchers and locals alike are hopeful that this royal structure will offer new insights into Myanmar's regal past, contributing to a fuller understanding of the region's complex and fascinating history. Scientists find mysterious forms of energy in Egypt's pyramids. In one of the most surprising and intriguing scientific developments in recent years, researchers have uncovered evidence suggesting that Egypt's Great Pyramid of Giza is capable of concentrating electromagnetic energy under certain conditions. This groundbreaking discovery not only deepens humanity's fascination with this ancient monument, but also raises new questions about the sophistication of the civilization that built it and the possible modern applications of the phenomenon. The study, carried out by an international team of researchers from Russia's ITMO University in collaboration with Laser Zentrum Hanover, used modern physics tools such as numerical modeling and multipole analysis to examine the pyramid's electromagnetic response. Specifically, their research focused on how the Great Pyramid reacts to electromagnetic waves, particularly within the radio wave spectrum ranging from 200 to 600 meters in wavelength. To their astonishment, they discovered that the pyramid's internal chambers, and even the area beneath its base, exhibited a unique capability to focus electromagnetic energy, particularly when excited at resonant frequencies.